Welcome. This video is going to take a look at something called an empirical formula. And an empirical formula is an important piece between going from an unknown compound to its known molecular formula. So empirical formula allows you to work backwards from analyzing what elements are in your unknown compound to finding the actual molecular formula of the unknown. And it's going to be important in forensics and toxicology, all those crime shows you see. It's also important in pharmaceuticals, cosmetics, food, etc. In fact, virtually any industry that makes some kind of product, other companies are going to be trying to figure out the empirical formula and then the molecular formula for whatever that product is, whether it's a pharmaceutical that they're trying to develop a generic version for, or if it's a new flavor of yogurt that Dannon's trying to mimic what Yoplait is doing. This happens all the time in industry. So an empirical formula is defined as a chemical formula that shows the simplest ratio of the elements in the compound rather than the actual number of each kind of atom. Okay, so it might not be the actual number of each kind of atom, but it is the simplest ratio. So it can be found if you know the mass or percent of each element in an unknown compound, and it doesn't matter if you know the mass of each element or if you know the percentage, but it has to be the same. Either know the masses of all the elements or know the percents of all the elements. And it means now you have to change your grams of each element back to moles. And this is the ever-going conversion in chemistry. When you're working in the lab, you measure things in mass, but when you actually work with the chemical formulas and with the equation, then you need it in moles. So if you're starting with the unknown, you're going to have your grams and you need to convert it to moles. And again, the empirical formula may or may not be the same as the actual formula, but it's the right ratio. For example, C14H10O4 is the molecular formula for something called benzoyl peroxide. But the empirical formula would actually be C7H5O2 because you can divide each of those subscripts by 2 to get a simpler ratio. So I've come up with a 3-step process I like to use to determine the empirical formula. Step 1 is to divide the mass or the percent of each element by its molar mass to find the moles of each. And if it's given in percents, you just assume it's a 100-gram sample and you change each percentage to grams for that element. Just ignore the percent, think grams, and go from there on step 1. Step 2, write the chemical formula using the moles of each element that you got in step 1. Now this is going to look funny because these are probably going to be decimals, so round to 3 decimals and go with it. Then step 3, divide each of the subscripts with your silly formula for number 2 by the smallest ratio you got, by the smallest molar amount that you got. And this will give you new subscripts. And hopefully your answers will all be whole numbers, or you'll have nice decimals. And what I mean by nice decimals is it'll be something that's a common fraction, like it'll be 0.2498 or right about 0.25, which is 1/4. Or it'll be very close to 0.33 or 0.66, 0.7, because that's 1/3 and 2/3. Or it might be near 0.5 or 0.75. That simply means you've got a fraction of 1/2, 1/3, or 1/4. So if you have a fraction, you're going to multiply the whole thing by the denominator to make the denominator go away. And if it's a whole number, then you have your subscripts and you're finished. So let me work a couple examples and show you what I'm talking about. My first example says, find the empirical formula if a compound contains 40% sulfur and 60% oxygen. So step 1, I'm going to change these each to moles. But the first thing I have to do is assume I have 100 grams of this stuff, so 40 grams would be sulfur and 60 grams would be oxygen. So if I have 40 grams of sulfur, using dimensional analysis, I look on my periodic table and I see 1 mole of sulfur has a mass of 32.07 grams, which means I have a little over a mole of sulfur, 1.247, and I hang on to 3 decimal places throughout this, regardless of what my sig figs are, because I don't have to worry about sig figs till my final answer. So this is my moles of sulfur. And then my 60 grams of oxygen, using dimensional analysis, I want moles. I have grams, and according to the periodic table, it's 16 grams in a mole. So 60 divided by 16 is 3.75. And if I want 3 decimals, I'm going to have to put a 0 there because that worked out even. It says moles of oxygen. So that's step 1. Step 2 is to rewrite this as a formula, S 1.247O3.75. And as I predicted, it looks kind of odd because we don't usually see decimals in our formulas. So then I go on to step 3, and I go ahead and divide each of them by the smaller decimal, which is the 1.247. And when I do that, I get S1, and O now becomes 3.75 divided by 1.247. It's 3.007, which is close enough to say that my formula must be SO3. Okay, so that's an example where it worked out to whole numbers. So on this try it, go ahead and see if you can get through steps 1, 2, and 3. Pause it, and I will work through those steps as well, and we'll see if we come up with the same empirical formula. So again, step 1, I'm going to change these to grams because that would add up to 100 grams of this substance. A lot of times I put my symbol out here so I remember which one I'm dealing with. I've got 10.89 grams of magnesium. Looking on the periodic table, I see 1 mole of magnesium weighs 24.31 grams. So this isn't quite half a mole. It's 0.448 moles of magnesium. My chlorine, 31.77 grams, and 1 mole of chlorine has a mass of 35.45 grams. So I got a little less than a mole of chlorine. 0.896 moles of chlorine. And then oxygen is 57.34. And by now you probably remember oxygen 16 grams per mole. So I'm going to have just less than 4 moles here. 57.34 divided by 16 is 3.584 moles of oxygen. So that's step 1, get them all into molar amounts. So step 2, a very funny looking formula, Mg.448 Cl 0.896 and O 3.584. So if I go right on to step 3, I divide each of these by 0.448 and see if I get whole numbers or recognizable fractions. And when I do that, Mg, of course, is going to become 1. Make that one a little more obvious. Cl 0.896 divided by 0.448 is going to come out right on the money with 2. And oxygen 3.584 divided by 0.448 comes out exactly to 8. So I would rewrite this as just Mg Cl2O8, or you maybe remember that there's a polyatomic ion ClO4, so this would actually be Mg ClO4 parentheses 2, but Mg Cl2O8 would be its simplest empirical formula. Okay, so on this last one, you're going to end up with a fraction, I believe, on this one. So go ahead and pause and see what you can come up with. See if you can figure out what to do with the fraction. So I have 18.42 grams of nitrogen. So using my table, I see 1 mole equals 14.01 grams. So I have a little more than a mole of nitrogen. 18.42 divided by 14.01 is 1.315 moles. And again, hang on to 3 decimals, otherwise your rounding can get a little goofy, especially if there is a fraction involved. The oxygen is 31.58 grams, and 1 mole of oxygen is 16 grams. It's going to be close to 2, but not quite. So 31.58 divided by 16 gives me 1.974. So now in step 2, when I write my formula, I've got N 1.315, O 1.974, and when I divide by 1.315, I end up with, in step 3, N1, but my O, 1.974 divided by 1.315, that's 1.501. So what that's telling me is that my ratio is really 1 to 1.5. Or if I want that in whole numbers, that's really the same as 2 to 3. So how do I get rid of that? Well, if this is 1.5, if I multiply the whole thing by 2, that should take care of the denominator in 1.5, and it leaves me with N2O3. And that's an intro to empirical formulas.